There is a point in the western Pacific Ocean where the sea surface temperature climbs above 28 degrees Celsius, and the atmosphere above it begins to behave like a living engine. Not metaphorically, thermodynamically. Water evaporates at a rate that would drain an Olympic swimming pool in seconds. That vapor rises, cools, condenses, and releases the latent heat locked inside every molecule. That heat warms the surrounding air. Warmer air rises faster. More surface air rushes in to replace it, and the whole system begins to spin. Not because of wind, not because of chance, but because the Earth itself is rotating beneath it, dragging the Coriolis force across every cubic meter of moving air on the planet. The spin is not optional. It is a consequence of physics. What emerges from that process is the most powerful, sustained weather system that Earth's atmosphere is capable of producing. A tropical cyclone at its maximum intensity carries more energy in a single day than the total electricity consumed by the entire United States in a year. That is not a rhetorical flourish. The numbers are documented and peer-reviewed. A mature supertyphoon releases heat at a rate of approximately 5 to 20 exajoules per day. 1 exajoule is 10 to the power of 18 joules. The largest nuclear weapon ever detonated by humanity, the Soviet Tsar Bomba, released approximately 210 petajoules of energy. A single supertyphoon, over the course of its peak intensity, releases the equivalent of hundreds of those devices, not in an explosion, but in an unrelenting, organized thermodynamic process sustained over days. The word supertyphoon is not informal. It is a precise meteorological classification. The Joint Typhoon Warning Center, operated by the United States Navy and Air Force, designates a tropical cyclone a supertyphoon when its maximum sustained wind speeds reach or exceed 130 knots. That is approximately 150 miles per hour or 240 kilometers per hour. At that threshold, the storm is no longer a weather event in the ordinary sense. It is a planetary-scale fluid dynamic system operating at the edge of what Earth's atmosphere can physically sustain. To understand what that wind speed means at the scale of a human body, consider this. At 70 miles per hour, wind is already sufficient to tear shingles from rooftops and topple freight trucks on highways. At 150 miles per hour, the wind pressure on a flat surface is not linear. It scales with the square of velocity. That means wind at 150 miles per hour exerts roughly 4.5 times the pressure of wind at 70 miles per hour. A wall of air moving at that speed carries enough momentum to collapse reinforced concrete structures and accelerate debris to speeds lethal at distances of hundreds of meters. The storm now tracking toward the United States did not materialize from nothing. It was born in the warm waters of the Western Pacific, a region meteorologists call the Typhoon Basin, the most active tropical cyclone basin on Earth. More than 30% of the world's tropical cyclones form there, in a region of ocean stretching from the Philippines east to the dateline. The basin's extraordinary productivity is not accidental. The Western Pacific sits beneath one of the most persistent atmospheric structures on the planet, the Western Pacific Subtropical High, a massive high-pressure ridge that steers developing systems westward across the open ocean, giving them hundreds or thousands of miles of warm water to feed on before they encounter land or cooler sea surface temperatures. What makes this particular system exceptional, what pushed it into the supertyphoon category and set it on a trajectory toward the continental United States, is a convergence of conditions that atmospheric scientists have been tracking with increasing concern. Sea surface temperatures across a broad corridor of the Pacific are running significantly above the long-term average. The ocean does not heat uniformly. It stratifies in layers, with warmer water sitting above cooler, denser water. The depth of that warm surface layer matters enormously for tropical cyclone intensification. When a storm passes over shallow, warm water, its own circulation stirs up cooler water from below, effectively cooling its own fuel supply and limiting intensification. When the warm layer extends deep, 30, 40, 50 meters below the surface, the storm can extract heat without cooling the ocean beneath it. In this case, that warm layer is unusually deep. The storm fed on it without resistance. Rapid intensification is the most dangerous and least predictable phenomenon in tropical meteorology. It is defined as an increase in maximum sustained winds of at least 35 knots, roughly 40 miles per hour, within a 24-hour period. The physics behind it are well understood in broad terms, but the precise timing and magnitude remain among the hardest problems in operational weather forecasting. It requires a specific alignment, anomalously warm and deep ocean heat content, low vertical wind shear in the atmosphere, sufficient moisture in the mid-levels of the troposphere, and an undisturbed large-scale environment that allows the storm's outflow, the exhaust of the engine, to ventilate freely into the upper atmosphere. When those conditions align, intensification can happen faster than models predict, faster than evacuation timelines allow. This storm intensified rapidly. Over a 36-hour window, it went from a tropical storm, winds below 64 knots, to a super typhoon. That rate of intensification placed it among the most extreme cases observed in the modern satellite era. The minimum central pressure, the single number that best captures a cyclone's overall intensity, dropped to levels recorded only a handful of times in the historical record for the Pacific Basin. Central pressure is worth pausing on. Sea-level atmospheric pressure across most of the planet hovers near 1,013 hectopascals. That is the weight of the entire column of air above every square meter of Earth's surface, roughly 10 metric tons pressing down per square meter. In a powerful hurricane or typhoon, that pressure drops dramatically at the center. In the strongest storms on record, it has fallen below 870 hectopascals. That pressure difference between the eye of the storm and the surrounding atmosphere is the engine of the entire circulation. Air rushes inward at the surface toward that low-pressure core, rises through the eye wall in towering cumulonimbus convection, reaching 15 kilometers into the atmosphere, then spreads outward at altitude. The lower the central pressure, the steeper the pressure gradient and the faster the surface winds that result. There is a persistent myth that the most dangerous part of a landfalling tropical cyclone is the wind. News coverage reinforces this. Wind speed is the primary number reported, the primary basis for categories on the Saffir-Simpson scale. Wind is visible in footage. Wind is dramatic. But the scientific literature is unambiguous on this point. Historically, the majority of tropical cyclone fatalities in the United States have come not from wind, but from water. Specifically, from storm surge, the dome of ocean water pushed ashore by the storm's winds and low pressure, and from freshwater flooding caused by extreme rainfall. Hurricane Katrina's catastrophic death toll in 2005 was overwhelmingly a storm surge event. Hurricane Harvey's devastation of Houston in 2017 was primarily a rainfall and flooding event. A super typhoon making landfall on the U.S. coastline does not need to maintain Category 5 wind speeds at the moment of landfall to be catastrophic. It needs only to pile enough water in front of it and to stall. The storm is moving. Its forward speed, its track, its interaction with the mid-latitude jet stream as it approaches the coast, all of these variables are now under continuous analysis by the National Hurricane Center, the National Weather Service, and dozens of university research groups running ensemble forecast models. Those models are not in perfect agreement. They never are at extended range. The uncertainty cone, the official representation of forecast track uncertainty, widens significantly beyond 5 days. And this storm is still days from any potential landfall. That uncertainty is not a failure of science. It is an honest representation of the chaotic nature of atmospheric dynamics. The atmosphere is a nonlinear system. Small perturbations in initial conditions propagate and amplify. Edward Lorenz described this mathematically in the 1960s and fundamentally changed how scientists think about predictability. The same physical principles that govern a super typhoon's future track also set hard limits on how precisely any forecast system can predict it. What modern ensemble modeling does, running dozens of slightly different simulations and examining the spread of outcomes, is the most rigorous approach science has to quantifying that irreducible uncertainty. What is not uncertain is the storm's current state. It is real. It is measured. It is documented by reconnaissance aircraft, by satellite microwave imagery, by GPS dropsondes released from aircraft flying directly through the eye wall. The data is not ambiguous, and the physics of what happens when a super typhoon encounters a coastline, when thousands of kilometers of organized atmospheric circulation meet shallow water and land, is among the most well-studied problems in the entire field of atmospheric science. The ocean is already rising ahead of it. Tropical cyclones die over land. That is the foundational assumption embedded in most people's mental model of these storms. And it is only partially true. The mechanism behind it is real. Cut a storm off from its oceanic heat source, increase surface friction, and the thermodynamic engine begins to starve. Wind speeds drop, the pressure gradient weakens, the system fragments. For the vast majority of typhoons that form in the Western Pacific, this is exactly what happens. They track westward, make landfall somewhere across the Philippine archipelago, Vietnam, southern China, or Japan, and dissipate within hours to days of losing ocean contact. The Pacific Ocean, for most of recorded history, has served as a geographic firewall, a barrier that consumes these systems before they can reach North America. This storm did not follow that path. The jet stream is a river of air. That description is not metaphorical. It behaves with genuine fluid dynamics, complete with meanders, eddies, and currents that can accelerate to over 300 kilometers per hour at altitudes between 9 and 12 kilometers above sea level. It flows from west to east across the mid-latitudes of both hemispheres, driven by the temperature contrast between the cold polar air masses and the warmer subtropical regions beneath. In normal circulation patterns, the jet stream acts as a barrier to tropical systems attempting to move poleward. Its strong wind shear, the change in wind speed and direction with altitude, tears apart tropical cyclone structure, disrupting the organized convection that sustains the eye wall. But the jet stream is not static. It meanders. Its path shifts north and south in large-scale wave patterns called Rossby waves, planetary-scale atmospheric undulations named after the Swedish-American meteorologist Carl Gustaf Rossby, who mathematically described them in the 1930s. When a Rossby wave amplifies significantly, the jet stream can buckle into exaggerated ridges and troughs. A ridge is a northward bulge of the jet. A trough is a southward dip. The pattern currently established over the Pacific is unusual. A strong ridge has built across the central Pacific, forcing the jet stream into a pronounced northward deviation. That ridge is acting as a steering mechanism, a wall of high pressure that is deflecting the storm's track away from a westward landfall in Asia and instead curving it northeast, then east, across the open Pacific. The open Pacific. Thousands of kilometers of warm, undisturbed ocean. No land to weaken it. No upwelling of cold water to starve it. Just a vast thermal reservoir and a steering pattern that is guiding it precisely toward the western coastline of North America. The question of why the jet stream has buckled in this particular configuration is not simple, and the honest answer is that atmospheric science is still developing a full mechanistic understanding of it. What is well documented is the correlation. As Arctic temperatures have risen at roughly 2 to 3 times the global average rate, a phenomenon called Arctic amplification, the temperature gradient between the poles and the tropics has weakened. That gradient is the primary driver of the jet stream's speed and stability. A weaker gradient produces a slower, more meandering jet stream, one that is more prone to amplified Rossby wave patterns and the kind of persistent ridges and troughs that lock weather systems in place or steer them along anomalous tracks. The research on this linkage remains an area of active scientific debate, with studies published in journals including Nature Climate Change and the Journal of Geophysical Research, presenting competing analyses of the observational record. What is not debated is the observational fact itself. The ridge is there, it is strong, and it is steering this storm. Extratropical transition is the process by which a tropical cyclone, moving into higher latitudes, begins to interact with the mid-latitude atmospheric environment and fundamentally restructures itself. In the tropics, cyclones are warm core systems. Their energy comes from the release of latent heat in deep convection, and they are warmest at their center at all levels of the troposphere. The temperature contrast that drives them is vertical, between the warm ocean surface and the cold upper atmosphere. As a tropical cyclone moves poleward, it encounters a different energy regime. Mid-latitude weather systems are cold core. They derive their energy from horizontal temperature contrasts, the baroclinic instability between cold polar air masses and warm subtropical air. When a tropical system reaches latitudes where those horizontal temperature gradients are significant, something remarkable can occur. Rather than weakening, The storm can tap into this new energy source and actually re-intensify. Extratropical transition is not a weakening process. It is a structural metamorphosis. The storm's symmetric, eye-centered wind field begins to acquire asymmetry. A warm front develops ahead of the system, a cold front trails behind it. The maximum winds, which in a tropical cyclone are concentrated within the eye wall close to the center, begin to spread outward as the system expands in horizontal scale. A tropical cyclone with maximum winds of 150 miles per hour concentrated within 50 kilometers of the center is a different hazard than a post-transition system with winds of 100 miles per hour distributed across a radius of 500 kilometers. The total energy in the second system is substantially larger. The area exposed to damaging winds is an order of magnitude greater. Historical precedent exists, and it is instructive. In October of 1991, Typhoon Fred underwent extratropical transition in the Western Pacific and eventually contributed to the development of what became known as the perfect storm, the nor'easter that combined with the remnants of Hurricane Grace to produce waves estimated at 30 meters height in the open Atlantic. In 2018, Typhoon Trami and Typhoon Kongray both underwent partial extratropical transitions before making landfalls in Japan, with Kongray producing rainfall totals exceeding 500 millimeters in 24 hours in parts of the Korean peninsula. The process is documented, repeatable, and physically understood. What varies is the intensity and timing of the transition, and how much of the tropical characteristics, particularly the concentrated core winds, are preserved as the storm moves into the mid-latitudes. The track models are now showing something that forecasters are watching with particular attention. The storm may be approaching the California coast, or, in some ensemble members, the Pacific Northwest, at a stage in its extratropical transition where it retains significant tropical characteristics while simultaneously tapping into baroclinic energy. That combination is not well represented in the historical database. There are very few analogs. The western coast of North America is not a typhoon coastline. Its coastal infrastructure, its building codes, its emergency management frameworks were not designed around this threat. The Atlantic Hurricane Corridor, the Gulf Coast, the Carolinas, Florida, has a century of institutional memory built around tropical cyclone preparedness. The Pacific Coast does not. Storm surge modeling for a Pacific Coast typhoon landfall is itself an area of active research precisely because the scenarios are so rare. The coastal geometry of the Pacific Coast differs fundamentally from the Gulf of Mexico. The continental shelf off California is narrow. In some areas, the seafloor drops precipitously within kilometers of the shoreline. A narrow shelf limits storm surge buildup compared to the broad, shallow shelf of the Gulf, where water can be pushed ahead of a storm for hundreds of kilometers in relatively shallow water. But the Pacific Coast has other vulnerabilities: coastal bluffs, river mouths, low-lying bay communities, and a network of river systems that can carry catastrophic freshwater flooding inland if rainfall totals are extreme. The rainfall threat from a landfalling Pacific typhoon is, if anything, more concerning than the wind. An atmospheric river, a long, narrow corridor of enhanced water vapor transport in the atmosphere, can form in association with an approaching tropical or post-tropical system. California and the Pacific Northwest have direct experience with atmospheric rivers. They are responsible for the majority of the region's annual precipitation and, in extreme cases, for catastrophic flooding. A tropical system making landfall on the Pacific coast while interacting with an established atmospheric river pattern would inject an extraordinary quantity of tropical moisture into that corridor. Rainfall totals in such a scenario could exceed those of any event in the modern instrumental record for the affected region. The Oroville Dam crisis of 2017, triggered not by a tropical storm but by an exceptionally wet winter, demonstrated what extreme rainfall does to California's water infrastructure. The spillway of the tallest dam in the United States was damaged by flows it was not designed to handle, threatening downstream communities holding nearly 200,000 people. That event happened during a normal, if extreme, California winter storm sequence. The atmospheric dynamics now approaching contain a moisture reservoir that dwarfs what California winters typically deliver. Meteorologists have a term for what happens when multiple hazards compound simultaneously: a cascading event. Wind, surge, rainfall, flooding, landslides on fire-scarred hillsides, each one manageable in isolation within the range of historical experience. Together, in the right geographic and seasonal conditions, they interact in ways that amplify total impact far beyond what any single hazard model predicts. The storm's central pressure is still falling. Every tropical cyclone is, at its core, a heat engine. The thermodynamic principles governing it are the same ones James Prescott Joule and Nicolas Léonard Sadi-Carnot worked out in the 19th century. The same physics that describes a steam turbine or an internal combustion engine. Energy flows from a hot reservoir to a cold reservoir, and in the process, mechanical work is extracted. In the case of a tropical cyclone, the hot reservoir is the warm ocean surface. The cold reservoir is the upper troposphere, at altitudes around 15 kilometers, where temperatures fall to -70 or 80 degrees Celsius. The mechanical work extracted is the rotational kinetic energy of the wind field. The efficiency of this heat engine, what fraction of the available thermal energy gets converted into wind, depends on the temperature difference between those two reservoirs. The larger the contrast, the more efficient the engine. Cary Emanuel, a meteorologist at the Massachusetts Institute of Technology, formalized this framework in the 1980s with a concept he called the maximum potential intensity, a theoretical upper bound on how strong a tropical cyclone can become, given specific ocean surface temperatures and atmospheric conditions. The formula is elegant in its construction. It treats the tropical cyclone as a Carnot heat engine and derives the maximum wind speed from first principles of thermodynamics. What Emanuel's work revealed is that the theoretical speed limit is not arbitrary. It is set by ocean temperature and the temperature of the outflow layer at the top of the storm. Raise the ocean temperature by 1 degree Celsius, and the maximum potential intensity increases by several meters per second. The relationship is nonlinear at the upper end. Small increases in sea surface temperature near the warm end of the range produce disproportionately large increases in theoretical maximum intensity. The current sea surface temperature anomalies along this storm's track are not 1 degree above average. In several corridor segments, they are running 3 to 4 degrees Celsius above the long-term mean. That is not a marginal perturbation. It is a fundamental shift in the energy ceiling available to the storm. Wind speed in a tropical cyclone is not uniform. It varies radically with distance from the center, and the relationship between that variation and the storm's internal dynamics is one of the more counterintuitive aspects of tropical meteorology. The radius of maximum winds, the ring around the eye where wind speeds peak, is typically located between 20 and 50 kilometers from the center in an intense tropical cyclone. Inside that ring, moving toward the eye, winds actually decrease. The eye itself is a region of relative calm, descending air, broken cloud, sometimes blue sky visible overhead. This descent is forced by the dynamics of the eye wall convection. The rising air in the eye wall must be compensated by sinking air somewhere, and the inside of the eye is where that compensation occurs. The sinking compresses and warms the air adiabatically, producing the anomalously warm temperatures at the storm center that define it as a warm core system. To stand inside a typhoon eye, as reconnaissance crews have done hundreds of times, is to experience one of the more disorienting juxtapositions in the natural world. Relatively calm air overhead, a circular wall of towering thunderstorms surrounding you on all sides, rising to 15 kilometers, and beyond that wall, winds that can remove a reinforced structure from its foundation. The diameter of a supertyphoon eye is typically between 30 and 60 kilometers. An analogy: if the eye were placed over Manhattan, the eye wall would reach from roughly the northern edge of the island to the southern tip and extend outward into New Jersey and Brooklyn simultaneously. The calm center, by that scale, is smaller than Central Park in the context of the total storm. Outside the radius of maximum winds, wind speed decreases with distance from the center following an approximate power law relationship, but the total wind field of a large supertyphoon extends far beyond the inner core. Tropical storm force winds, defined as sustained speeds above 63 kilometers per hour, can extend 500 kilometers or more from the center of a major storm. Hurricane force winds above 119 kilometers per hour can extend 200 kilometers or more. At landfall, this means that a coastline can experience sustained hurricane-force winds for hours before the eye wall arrives, and for hours after it passes. The damaging wind event is not a single moment. It is an extended siege. The eye wall replacement cycle is among the most remarkable self-organized phenomena in atmospheric science. In intense tropical cyclones, a secondary ring of deep convection sometimes forms outside the primary eye wall, at a radius of perhaps 50 to 100 kilometers from the center. This outer ring gradually organizes, strengthens, and contracts inward. As it does, it cuts off the inflow of warm, moist boundary layer air to the inner eye wall, starving it of its fuel supply. The inner eye wall weakens and dissipates. The outer ring contracts to the center and becomes the new eye wall, typically at a slightly larger radius. During this process, which can last 12 to 48 hours, the storm undergoes a temporary weakening phase, followed by re-intensification. Storms that complete eye wall replacement cycles can emerge with a larger wind field radius, more destructive area at landfall, even if their peak intensity is marginally lower than before the cycle. This storm has undergone at least one eye wall replacement cycle already during its life over the Western Pacific. Microwave satellite imagery, which penetrates the upper cirrus canopy and directly images the deep convective structure of the eye wall, showed the classic concentric ring pattern, then the dissolution of the inner ring, then the contraction of the outer ring to the center. The storm's radius of maximum winds expanded in the process. The area subject to its most destructive winds grew. Rainfall in tropical cyclones is governed by a different set of physics than wind. While wind intensity scales primarily with sea surface temperature and atmospheric moisture, rainfall totals at any given location depend critically on storm translation speed, how fast the system is moving across the ground. A storm moving at 20 kilometers per hour over a point will deliver its rain over a much shorter time than one crawling at 5 kilometers per hour. The total rainfall accumulation is approximately inversely proportional to translation speed. Halve the forward speed, double the rainfall total, all else being equal. Hurricane Harvey's catastrophic rainfall over Houston in 2017, which reached approximately 150 centimeters in some locations over 4 days, occurred because the storm stalled nearly stationary over the Texas coast, held in place by a weak steering flow. The forecast models for this storm's landfall show a slowing of its forward speed as it approaches the coast. The steering ridge pattern that has guided it across the Pacific is forecast to weaken as the storm approaches the coastline, leaving it in a zone of weak, large-scale flow. Reduced translation speed over the coast means the storm's full moisture delivery system, drawing on the anomalously warm, moist air mass it has traversed for thousands of kilometers, could concentrate its rainfall on a relatively narrow geographic corridor for an extended period. The amount of water vapor a parcel of air can hold increases exponentially with temperature, following the Clausius-Clapeyron relation, roughly a 7% increase in saturation water vapor content per degree Celsius of warming. The boundary layer air feeding into this storm has traveled over ocean surfaces 3 to 4 degrees above average. That air carries substantially more precipitable water than historical analogs. The storm is not just a wind event or a surge event. It is a water delivery system of extraordinary capacity. The physics of landslide triggering on the hillsides and mountains of the Pacific coast adds another layer. The coastal ranges of California and the Cascades are geologically young, steep, and composed in many places of poorly consolidated material. Wildfire history across the region has left extensive areas of hillside with destroyed root systems and hydrophobic soil layers. Terrain that generates rapid runoff and debris flows at rainfall intensities far below what this storm's outer bands alone are forecast to produce. The interaction between extreme rainfall and fire-scarred terrain is not speculative. It produced the Thomas Fire debris flows in Montecito, California in January of 2018, killing 23 people in the middle of the night with a wall of mud and boulders moving at speeds too fast to outrun. The water cycle, at planetary scale, is simply the redistribution of solar energy. Every kilogram of water evaporated from the ocean surface carries with it approximately 2,500,000 joules of latent heat, the energy absorbed during the phase transition from liquid to vapor. When that vapor condenses in the eye wall convection of a supertyphoon, Every kilogram releases that same energy back into the atmosphere. A supertyphoon precipitating 2 centimeters of rain per hour over a circular area 500 kilometers in radius is condensing and releasing latent heat at a rate that staggers any intuitive sense of scale. The numbers require scientific notation to write comfortably. That energy has been building in this storm for days. It has not yet been released against a coastline. The reconnaissance aircraft is still flying. In September of 2018, Supertyphoon Mangkhut made landfall in the northern Philippines, with maximum sustained winds of 265 kilometers per hour. It was the strongest landfalling tropical cyclone of that year globally, and it had been tracked with reasonable accuracy by numerical weather prediction models for nearly a week before impact. The forecast was good, the warnings were issued, and still, the storm killed over 130 people across the Philippines, China, and Hong Kong, caused approximately $4 billion in damage, and produced storm surge heights of up to 6 meters in coastal communities that had been told to evacuate and, in many cases, did not. That gap between accurate scientific prediction and realized human outcome is one of the defining problems of modern meteorology. It is not a failure of physics. It is a failure at the interface between science and society, between forecast and action, between warning and behavior. The forecasting of this storm, however, has not been straightforward, and the scientific community knows it. Numerical weather prediction operates by dividing the atmosphere into a 3-dimensional grid of cells, assigning observed values of temperature, pressure, wind, and humidity to each cell, then solving the equations of fluid dynamics and thermodynamics forward in time. The resolution of that grid determines what physical processes can be explicitly represented. The European Centre for Medium-Range Weather Forecasts, ECMWF, based in Reading, England, runs the model widely considered the most skillful in the world for mid-range forecasting. Its operational deterministic model runs at a horizontal resolution of approximately 9 kilometers globally. Its ensemble system, which runs 51 slightly perturbed versions of the same model to quantify forecast uncertainty, runs at 18 kilometers. The American Global Forecast System, operated by the National Oceanic and Atmospheric Administration, runs at comparable resolution. The United Kingdom Met Office, the Japan Meteorological Agency, the Canadian Meteorological Centre, all maintain competitive global models. They are extraordinary scientific instruments, ingesting millions of observations per day from radio sondes, commercial aircraft, ocean buoys, GPS satellites, and polar orbiting weather satellites, assimilating them into a coherent 3-dimensional picture of the current atmospheric state and projecting that state forward. For this storm, the models diverged. Not slightly, significantly. At 5 days before the forecast landfall window, the ECMWF ensemble showed a broad spread of track solutions ranging from a northern California landfall to a track that recurved sharply northward and made landfall in Oregon or Washington. The American GFS ensemble was clustered slightly further south, with its mean solution pointing toward the central California coast. The divergence between the two flagship global models at medium range is not unusual for Pacific systems. The typhoon basin is data-sparse compared to the Atlantic, and small errors in the initial conditions propagate rapidly in a chaotic system. But the magnitude of the track uncertainty in this case was larger than typical, and it had a specific cause that took forecasters several days to identify. The ridge pattern steering the storm, the anomalous high-pressure system that had blocked the storm's westward progression and curved it toward North America, was itself evolving. Its eastern edge, the boundary that would ultimately determine whether the storm tracked toward California, Oregon, or Washington, was sensitive to the behavior of a separate mid-latitude trough developing over the Gulf of Alaska. That trough was interacting with the ridge in ways that slightly different model solutions handled differently. A trough that eroded the ridge slightly faster would push the storm track southward. A trough that arrived slightly later would allow the ridge to persist and steer the storm further north. The difference in landfall latitude between these solutions was over 1,000 kilometers. The difference in impact, which communities face the eye wall versus the less intense outer bands, was the difference between catastrophe and a severe but manageable storm. This sensitivity to a feature thousands of kilometers away from the storm itself illustrates a concept that atmospheric scientists call teleconnection. the capacity for atmospheric anomalies in one region to influence weather patterns in a geographically remote region through the propagation of Rossby waves and large-scale pressure pattern interactions. The Gulf of Alaska Trough and the Pacific Steering Ridge were not independent features. They were part of the same planetary scale wave pattern, and the storm was threading through the interaction zone between them. What broke the forecast deadlock was not a model improvement. It was data. Specifically, it was a targeted observing mission conducted by NOAA's Gulfstream VSP aircraft, a high-altitude jet capable of flying at 13 kilometers altitude, above most of the weather it is studying. These missions, called synoptic surveillance flights, are specifically designed to sample the atmospheric environment surrounding a tropical cyclone at altitudes where global model data is sparse, dropping GPS dropsondes at regular intervals to measure wind, temperature, and humidity through the full atmospheric column. The observations from these dropsondes are transmitted in real time via satellite to NOAA's Environmental Modeling Center and assimilated directly into the next model run. The synoptic surveillance mission targeting the steering environment of this storm was conducted approximately 96 hours before the forecast landfall window. The dropsondes sampled the Gulf of Alaska Trough structure in detail that the routine observing network could not provide. When those observations were assimilated, both the GFS and the ECMWF ensemble solutions tightened dramatically. The spread of track solutions narrowed. The two models converged toward a solution. The convergence pointed toward the Northern California coast. The specific dynamics of what happens when a storm of this intensity encounters the coastal topography of Northern California are not well studied, because a storm of this type has not made landfall there in the modern era of scientific observation. The coast ranges run parallel to the shoreline, their ridges oriented north-northwest to south-southeast, rising to between 1,000 and 2,000 meters within 50 kilometers of the coast. These ranges act as an orographic barrier. As the storm's moisture-laden air is forced upward over the ridges, it cools, condenses, and produces extreme precipitation enhancement on the windward slopes. The rainfall totals on the windward side of an orographic barrier during a major landfalling storm can be 2 to 3 times higher than at the coast itself. Inland of the coast ranges, the Central Valley, a flat agricultural basin approximately 700 kilometers long and 80 kilometers wide, flanked on its eastern side by the Sierra Nevada, acts as a funnel for both wind and water.
Gap flows, where wind accelerates through mountain passes into the valley, can produce localized wind speeds well above the regional average. Flooding in the valley's river systems, the Sacramento River in the north, the San Joaquin in the south, propagates downstream over hours to days, threatening communities far from the coast that may perceive themselves as outside the storm's direct impact zone.
The Sacramento-San Joaquin Delta, where both river systems drain into San Francisco Bay before reaching the Pacific, is among the most hydraulically complex and vulnerable pieces of infrastructure in the American West. It consists of approximately 70 interconnected islands, most of them below sea level, protected by roughly 1,700 kilometers of aging earthen levees, many constructed in the 19th and early 20th centuries. These levees were not designed to handle the combination of extreme upstream river flows, wind-driven wave action on the delta waterways, and elevated bay water levels from a Pacific storm surge arriving simultaneously. A cascading levee failure sequence in the delta during a major flood event is one of the scenarios that the California Department of Water Resources has modeled as a potential catastrophic outcome, not because it is inevitable, but because the physics permits it. The storm does not know any of this. It does not track toward California because of any property of California. It tracks there because the fluid dynamics of the atmosphere in late April of this year produced a ridge-trough configuration that happened to aim its steering flow at this particular coastline. The atmosphere has no preference. The Coriolis force has no agenda. The Clausius-Clapeyron equation does not negotiate. But what the science had not anticipated, what the models had not resolved until the synoptic surveillance data arrived, was the secondary intensification signal embedded in the storm's inner core structure. Microwave imagery from the DMSP F-19 satellite, acquired 48 hours before forecast landfall, showed evidence of a new convective burst developing within the existing eye wall. Deep convective towers, technically called hot towers, Cumulonimbus cells penetrating above 16 kilometers into the lower stratosphere were firing in the down-shear left quadrant of the eye wall, a pattern associated in the research literature with imminent rapid intensification events. Carey Emanuel's maximum potential intensity ceiling, given the sea surface temperatures beneath the storm's current position, was not yet reached. The storm had thermodynamic headroom to intensify further. The National Hurricane Center issued a special advisory. The storm was stronger than the landfall forecast had assumed, and it was still over open water. The coastline does not move. It has no capacity to absorb what is arriving. The rocky headlands of Northern California, shaped over millions of years by the subduction of the Juan de Fuca plate beneath the North American plate, by the slow, patient work of wave erosion and tectonic uplift, stand precisely where they have always stood. The Pacific has spent geological epochs carving them. Now the Pacific is coming for them with something different. Not the slow, patient erosion of normal wave action, but the concentrated, organized energy of a planetary heat engine at near-peak intensity, making its final approach to the coast. The storm's forward speed has slowed to approximately 12 kilometers per hour. At that translation speed, the leading edge of tropical storm force winds, speeds above 63 kilometers per hour, will pass over a given coastal point for roughly 16 hours before the eye wall arrives. That is 16 hours of sustained wind-driven wave action on top of a storm surge that has been building across hundreds of kilometers of open ocean fetch. Fetch is the distance over which wind acts on the water surface, transferring momentum from the atmosphere into the ocean. This storm has had thousands of kilometers of open Pacific fetch to build its wave field. The significant wave height, the average of the highest one-third of waves, in the storm's forward right quadrant has been measured by satellite altimetry at between 14 and 17 meters. Individual maximum waves in that sector, where wind waves and swell interact constructively, may reach 25 meters or higher. The wave field arriving at the California coast is not just the product of this storm's current winds. It contains swell components that were generated hundreds of kilometers back along the track, long-period energy that has been propagating ahead of the storm center for days. Long-period swell, waves with periods of 15 seconds or longer, travels faster than the storm itself and arrives at the coast before the wind field. It announces the storm's approach with a series of waves that carry energy from deep ocean to shallow water, compressing and steepening as the seafloor rises. The process is called shoaling. A wave that was 3 meters high in water 600 meters deep becomes 5 meters high in water 50 meters deep and continues to grow as the water shallows further until the wave's height exceeds approximately one-third of the water depth and the wave breaks catastrophically. On a normal Pacific winter day, the coastal surf along Northern California runs between 1 and 3 meters. In major winter swell events, the kind generated by powerful extratropical storms in the Gulf of Alaska, surf heights of 5 to 7 meters are documented at exposed breaks. What is now approaching belongs to a different category entirely. Modeled nearshore wave heights at exposed headlands range from 10 to 14 meters, values that have no recorded precedent in the modern coastal monitoring record for this coastline. Storm surge is distinct from waves. It is the quasi-static rise of mean sea level caused by two physical mechanisms acting simultaneously. The first is the inverse barometer effect. The reduced atmospheric pressure at the storm center allows the ocean surface to rise, at approximately 1 centimeter of sea level rise per hectopascal of pressure reduction. A storm with a central pressure of 900 hectopascals, 113 hectopascals below the standard atmospheric pressure of 1,013 hectopascals, produces an inverse barometer surge of roughly 113 centimeters at the center. The second mechanism is wind-driven setup. The storm's sustained winds push surface water in the direction of wind motion, piling it up ahead of the storm against whatever obstacle interrupts its movement, in this case, the coastline. The magnitude of wind-driven surge depends on wind speed, the length of water over which the wind acts, and critically, water depth. Shallow water concentrates the surge. The continental shelf geometry of the Northern California coast is less favorable for surge amplification than the Gulf Coast. But in coastal embayments, river mouths, and low-lying areas protected from open ocean wave action, surge heights of 2 to 3 meters above mean higher high water are forecast, arriving on top of a tidal cycle that places the timing of maximum surge within hours of high tide. The coincidence of extreme wave heights, storm surge, and high tide is not accidental. It reflects the storm's translation speed and the timing of its approach relative to the tidal cycle, a variable that forecast teams at the National Hurricane Center have been tracking specifically because the amplification effect of surge coinciding with high tide can add 1 to 2 meters to effective inundation levels compared to the same surge arriving at low tide. Rainfall has already begun. The storm's outer spiral bands, organized arcs of deep convection extending 300 to 400 kilometers from the center, have been moving onshore for 18 hours. These bands do not deliver uniform rainfall. They produce intense convective cells embedded within the larger stratiform rain areas, cells that can locally generate rainfall rates of 5 to 10 centimeters per hour for periods of 20 to 40 minutes before moving on. The cumulative effect of successive outer bands crossing the same terrain is a presaturation of the soil and stream systems. Catchments that would normally have some capacity to absorb rainfall are already near saturation before the core of the storm arrives. The Russian River watershed in Sonoma County is one of the most flood-prone river systems in California. Its watershed drains approximately 3,800 square kilometers of Coast Range terrain. The river has flooded repeatedly in the modern record, in 1986, in 1995, in 2017, and in the atmospheric river events of 2023. Its lower reach, where it turns south and then west before meeting the Pacific at Jenner, passes through the town of Guerneville, a community that sits in a natural flood bowl where the river canyon widens. The town's historical flood benchmark, the level at which significant inundation begins, is set by events that were considered extreme. The rainfall totals now accumulating in the upper watershed, combined with the antecedent saturation from the outer bands, have the Russian River rising at a rate that the National Weather Service's Advanced Hydrologic Prediction Service is tracking in real time, its forecast crests revised upward with each successive model update. The eye wall is now 50 kilometers offshore. At 12 kilometers per hour forward speed, it is 4 hours from the coastline. Within the eye wall, the wind field is structured around a phenomenon that atmospheric scientists call the boundary layer jet, a local wind speed maximum that occurs within the lowest kilometer of the atmosphere, below the altitude of most wind speed measurements from reconnaissance aircraft. The boundary layer jet forms because friction from the ocean surface slows the wind in the lowest tens of meters, but the inflow of air toward the low-pressure center draws fast-moving air downward from higher levels, creating a jet of maximum wind speed at roughly 500 meters altitude. At landfall, when the surface transitions from water to land and surface roughness increases abruptly, this boundary layer jet is disrupted. Some of the momentum from the jet is transferred downward to the surface in gusts, brief, intense pulses of wind that can exceed the sustained wind speed by 30 to 40%. A storm with sustained winds of 180 kilometers per hour at landfall can generate gusts exceeding 250 kilometers per hour in the boundary layer jet collapse zone. Structural engineering codes in California are calibrated against wind loads derived from historical data. The strongest winds in the modern California record at coastal locations are associated with offshore downslope windstorms, the Santa Ana winds and the Diablo winds, which can exceed 130 kilometers per hour in extreme events. Those are the wind speeds that California's coastal building stock has been implicitly engineered to survive. What is arriving exceeds that threshold by a factor that most of the existing building stock was never designed to accommodate. The interaction of the wind field with the Coast Range topography will produce an additional hazard that has no clear historical analog for this region. As the storm's circulation moves onshore and the surface wind field encounters the mountain barrier, it will generate trapped mountain waves, atmospheric gravity waves that propagate horizontally along the mountain ridge under certain stability conditions. These waves can focus wind energy on specific downslope locations with dramatic local amplification. They are documented in association with the Diablo wind events and with downslope windstorm events in the Rocky Mountain region, the Boulder, Colorado windstorms of 1972, where surface wind gusts of 209 kilometers per hour were recorded from a system that had not been forecast to produce such extremes. The Northern California coast ranges, oriented perpendicular to the oncoming storm flow, meet the conditions for trapped mountain wave excitation. The eye wall is 40 kilometers offshore. In the scientific literature on landfalling tropical cyclones, the period immediately preceding landfall is described with the clinical term peak impact window. It refers to the 3 to 6 hour period surrounding eye wall passage, during which the maximum simultaneous combination of wind, surge, and wave hazards are experienced at any given coastal point. The term is precise. It is measured. It does not capture the physical reality of what it describes. The complete temporary reorganization of a coastline by atmospheric and oceanic forces operating at scales that dwarf anything in the historical experience of the region. The storm has not yet made landfall. The physics are already executing. The storm made landfall. That sentence contains an entire physics textbook compressed into 4 words. The eye wall crossed the coastline. The surface roughness transition from water to land disrupted the boundary layer in flow. The storm began the process of losing its oceanic energy source, and the organized circulation that had persisted for thousands of kilometers of open Pacific began, incrementally, to unravel. It did not unravel quickly. A storm system of this scale carries enough internal energy, stored in the rotating wind field, in the latent heat of the moisture already ingested into the circulation, in the momentum of tens of thousands of cubic kilometers of moving air, to sustain damaging winds and catastrophic rainfall for 12 to 24 hours after the center crosses the coast. The ocean is gone, but the consequences of the ocean are not. The physical footprint of what passed over Northern California will be measurable for decades, not metaphorically, literally in the geological record. Coastal geologists working the California shoreline after major storm events document what they call storm deposits, layers of coarse sand, shell fragments, and marine debris deposited inland of the normal high tide line by surge and wave overwash. These deposits are preserved in coastal marsh sediment cores, interbedded with the organic peat layers that accumulate in normal years. By radiocarbon dating the organic material above and below a storm deposit, researchers can reconstruct the frequency of extreme coastal inundation events stretching back centuries before the instrumental record began. The sediment cores from Northern California coastal marshes already contain evidence of prehistoric extreme events, storms or tsunamis that left their signatures in the stratigraphy long before European settlement. What was deposited in the hours of this storm's landfall will join that record. Future researchers, core sampling these marshes in 50 or 100 years, will find a distinct layer. They will date it. They will measure its grain size and thickness. And the physics of what produced it, the Clausius-Clapeyron equation, the Coriolis effect, the thermodynamic efficiency of a warm core heat engine, will be legible in the sediment. The atmosphere does not remember. It has no capacity for memory. Within days of the storm's passage, the pressure gradient that sustained the circulation has relaxed. The warm ocean surface, temporarily cooled by the storm's own upwelling along its track, has begun rewarming from solar radiation and subsurface heat flux. The jet stream, which buckled to steer the storm toward North America, has returned toward a more zonal configuration as the Rossby wave pattern evolved. There is no scar in the atmosphere. The troposphere has no recording mechanism for what it just did. The ocean remembers slightly longer. The cold wake, the corridor of upwelled cold water left behind along the storm's track, persists for 2 to 4 weeks before thermal diffusion and surface heating erase it. Satellite sea surface temperature measurements can trace a storm's entire track across an ocean basin weeks after the storm itself has dissipated, reading the cold signature it left in the thermal structure of the upper ocean, the way a forensic scientist reads evidence. That cold wake is also a record of how much heat the storm extracted, of how deeply it mixed the ocean, of how much energy was converted from oceanic thermal reservoir to atmospheric kinetic energy, and ultimately deposited on a coastline. The total energy budget of a tropical cyclone landfall has been quantified in multiple published analyses. The numbers are staggering in their magnitude and sobering in their implication. The kinetic energy contained in the wind field of a mature supertyphoon at peak intensity is approximately 1.5 times 10 to the 18th joules. comparable to the total global electrical energy production for approximately a year and a half. The vast majority of that energy is dissipated in the final hours of landfall, transferred from the atmosphere to the surface through friction, structural loading, wave action, and rainfall. Buildings, trees, levees, hillsides, river channels, they are all receiving the dissipated energy of a planetary heat engine. The structures that fail are not failing randomly. They are failing precisely at the points where the local energy flux exceeded their design tolerance, which was itself calibrated against a historical baseline that this storm has now permanently revised. That revision of the historical baseline is one of the most consequential long-term scientific implications of events like this one. Building codes, flood insurance rate maps, coastal zone management regulations, dam safety standards, all of these are grounded in probability distributions derived from historical records. The concept of the 100-year flood, for instance, refers not to a flood that occurs exactly once per century, but to a flood level with a 1% annual probability of exceedance, derived from the statistical distribution of historical peak flow records. When a storm produces flows that exceed the historical maximum of record by a substantial margin, it does not simply represent the upper tail of the existing distribution. It provides new information about the true distribution, information suggesting the tail is heavier, the extreme events more probable, than the existing record implied. Every infrastructure standard calibrated against that historical distribution is to some degree now underbuilt for the actual hazard it faces. This is not a comfortable conclusion for engineers, planners, or policymakers. It implies that infrastructure considered adequate last year may be inadequate today, not because the infrastructure changed, but because the scientific understanding of the hazard it faces has been updated by direct observational evidence. The Sacramento-San Joaquin Delta Levee System, designed and maintained against a historical flood frequency record that predates this event, faces a reassessment. The stormwater management systems of coastal communities, designed to handle rainfall intensities derived from historical data, face a reassessment. The coastal setback lines that define where construction is and is not permitted, derived from historical erosion and inundation records, face a reassessment. Science operates precisely by this mechanism, the encounter with new data that forces a revision of prior beliefs. Thomas Bayes, the 18th century English mathematician and minister, formalized the logic of this updating process in a theorem that carries his name. Prior beliefs, expressed as probability distributions, are updated by new evidence to produce posterior distributions that better reflect reality. Every extreme event that exceeds prior expectations is a Bayesian update on the hazard distribution. The atmosphere is running an experiment. The observational record is the data. The scientific community's job is to update its priors. The North Pacific has produced supertyphoons for as long as the Pacific has existed in something resembling its current configuration, tens of millions of years. The specific atmospheric and oceanic conditions that allow a tropical cyclone to form, intensify, and sustain itself are not new. Warm ocean, cold upper troposphere, sufficient Coriolis force, low wind shear. These conditions have been satisfied repeatedly throughout the Cenozoic. What is new is the baseline state on which these natural dynamics are now operating. Global mean sea surface temperatures have risen approximately 0.9 degrees Celsius since the pre-industrial period. The deep warm layer in the western Pacific, the oceanic heat content reservoir that this storm fed on without resistance, has increased in depth and thermal energy content across multiple decades of Argo float measurements and XBT transect data. The theoretical maximum intensity ceiling that Kerry Emanuel's framework predicts, computed for the sea surface temperatures present along this storm's track, is higher than it would have been for identical atmospheric conditions operating on the ocean of 50 years ago. The individual event cannot be attributed solely to any single cause. Attribution science, the branch of climate research that quantifies the probability change of specific extreme events in a warming versus a counterfactual stable climate, does not work by simple assignment. It works by comparing the probability distributions. A specific storm of this intensity in the pre-industrial climate had some probability of occurring. In the current climate, that probability is higher. How much higher depends on the specific event, the specific region, and the specific hazard metric being evaluated. For tropical cyclone rapid intensification rates, for the depth of the oceanic warm layer, for the atmospheric moisture content, the direction of the probability shift is consistent across multiple lines of evidence and multiple independent research groups. The storms are not new. The conditions that amplify them are changing. The California coastline is approximately 1,350 kilometers long. It has been shaped by every storm, every earthquake, every tsunami, every season of wave erosion that has acted on it since the last major sea level change following the end of the Pleistocene glaciation, approximately 11,000 years ago. The human infrastructure built along it has been present for, at most, a few hundred years, a geological instant. The building codes, the coastal engineering, the flood maps, the infrastructure standards, they were calibrated against a slice of climate variability that now, demonstrably, does not fully represent the range of what the Earth's atmosphere can produce and direct at this coastline. The storm is dissipating over the interior. Its circulation is fragmenting over the mountain terrain, the eye wall structure destroyed by surface friction and the loss of oceanic energy supply. Its remnant moisture is being absorbed into the mid-latitude westerlies, carried eastward, eventually precipitated somewhere over the continent as ordinary rain. The energy it carried, extracted from the anomalously warm Pacific over days of intensification, organized by the Coriolis force into a rotating thermodynamic engine, delivered to a coastline in hours of eye-wall passage, has been returned to the Earth system. It has not been destroyed. Energy is never destroyed. It has been redistributed into the kinetic energy of floodwaters moving down river channels, into the potential energy of sediment deposited inland of the former shoreline, into the thermal energy of air that was compressed and warmed as it descended the lee side of the coast ranges, into the chemical energy of soils that will take years to restabilize on denuded hillsides. The Pacific is already warming again. The next convective cluster forming in the western Pacific Basin, a disorganized area of thunderstorms that the Joint Typhoon Warning Center has assigned an invest number in the past 24 hours, is being watched. The sea surface temperatures beneath it are above 28 degrees Celsius. The vertical wind shear in its environment is low. The oceanic heat content in that sector of the western Pacific, measured by the Argo Float Network and updated in near real time, shows a warm layer extending to 40 meters depth. The atmosphere does not pause. The ocean does not rest. The physics that organized one supertyphoon are organizing the conditions for the next one with the patient indifference of physical law. The same indifference with which a planet 4.5 billion years old regards the brief, urgent existence of the species currently trying to understand it.